after studying about this multiple roots, we'll move forward and we'll study about finite fields. So can you tell me what are finite fields? Finite fields is the one having a finite number of elements within it. A finite number of elements within it, right? This we have already studied a bit, a definition of finite field, and we have also seen few examples. But here we will see this topic in detail. So for that we will first study what are prime fields. So what is a prime field? A field is called prime field if it has no proper subfield within itself. So you can say in other words that it is formed by the intersection of the family of subfields. So suppose you have some larger field here, and these are smaller subfields which are like, these are some subfields, right, which are present in this field. Why they would cover each other? Because they will have the common element as the multiplicative and additive identity common to them, right? And we will say their intersection. So this would be their intersection. So this intersection would be a prime subfield. So what is a prime field? It is the field which has no proper subfield. For example, we have this field of rational numbers and this field Z modulo P, where P is a prime number. So these two, they are prime fields. Why? Because they are the smallest fields which do not have any proper subfield, because we know the proper subset of this set Q, that is the set of integers, and that is not a field. So this field of rational numbers do not have some kind of subfield within itself. So we can say it is the smallest, these are the smallest fields which could be available. So we can say these are the smallest fields. And moreover, this field of rational numbers and that of integers modulo P, that are the only kinds of field which are available as prime fields. How? We'll see that through an example. So firstly we'll prove that this integer modulo P, this is a prime field. So how this is a prime field? For that we will denote P as the prime subfield of ZP if possible. We have to prove that this ZP, this is a prime field. This we have to prove, right? So what we do, we assume that there is some field which is a subfield for this. Say P is a subfield for this, and we will try to prove that this P, that forms a prime field for ZP. So if possible, we denote this prime P by capital P, and now we will try to prove, if we are to prove that this is ZP is the prime field, that means we will prove that P is nothing but equal to ZP, because it is the smallest subfield which is present. So this is our aim here. So for that, because we have considered P to be the prime subfield of ZP, so that means we will say P is a subfield of ZP. So this is equation number 1. And next we will show that ZP is also contained in P. So if these two conditions are satisfied, so we will say that these two fields, they are equal, and then because P was prime subfield, our ZP, integers modulo P, is also a prime subfield. So this is what we are to prove. So for that, because P contains 1, why? Because it is a subfield, and subfield has the multiplicative identity within themselves. So that is true. So now, what is this P? P is the subfield for ZP, and how many elements are present in ZP? ZP has the elements 0 bar, 1 bar, 2 bar, and so on up to P minus 1 bar. So these are the modulo or equivalence classes in which all the elements are available. When you divide any integer with p, you get the remainder either as 0, either as 1 or 2 or 3 or up to p minus 1. So the only elements which are present in P are also these equivalent classes. Why? Because this is a subfield for ZP. So that is the case. So therefore we say, because all these elements are also a part of the ZP, therefore we say ZP is contained in P. So this is one thing. Another thing, because P is a subfield of ZP, that means P is contained in ZP. So from this equation 1 and equation number 2, we can conclude that they are equal. So from here we have shown that the ZP, that is a prime field. So let us see next example. Here we will prove that this field of rational numbers, that is Q is a prime subfield. So we will show that this is a prime subfield. So how can we prove this to be the prime subfield? So we will prove that it has some field P inside it, and we will denote this by the prime subfield. Now if we are able to prove that this P is nothing but equal to Q, the field of rationals, then because P was prime subfield, Q would also be a prime subfield. So according to this, how are the elements of this field of rationals represented? Like, they are represented in this form, m divided by n, where both m and n, they are integers, and this n should not be equal to m, or it should not be a multiple of n. In other words, we can say the GCD of m and n should be equal to 1. That means they should be co-prime to each other. So any element of Q that is of this form. So how can we denote the elements of P? Because P, that is a subfield of Q, so that means it would have the multiplicative identity within itself. So its multiplicative identity is 1. So how can we write m? M can be constructed by adding 1 how many times? M times. So when you add 1, the multiplicative identity m times, so you will have the element m has which is present in P, because 1 is present in P and P is a subfield. So when you add the elements of P, you will again get an element of P, and you have when you add this one n times, you will have n as the element which is also present in P, because it is a subfield. So now because m and n both are present in P and their GCD is not equal to 1, so we say that their division is also present in P. So that means every element of this kind, m upon m, which was present in Q, is also now present in P. So we say Q is a subfield of P. So this is condition number 1. But because we have assumed this P to be the subfield of Q, so that means P is contained in Q. So accordingly, from equation 1 and from equation 2, we can say that P is equivalent to Q. So this is the result, right?